So in the previous lectures, we've seen now three examples of using the ANOVA formulation in which the beta coefficients, the coefficients of your linear model, are the coefficients that generate the residual, that minimize the residual sum squared errors. And you can find those equations using this, you can find those parameters using this one equation, which again we think of as the equation to rule them all. Right? No matter how complicated your equation is, no matter how complicated your models are, no matter how many different independent variables you have, you can solve this equation to get the beta for coefficients that give you the minimized, that are guaranteed to give you the minimized sum squared error. So we can take advantage of the fact of the flexibility of this class of models, of the ANOVA models, to examine models on data, or to examine models that are more complicated than the simple models that we've seen so far. So the simple models that we've seen so far are the t-test, the linear regression, and the one-way ANOVA, which is like a t-test but with multiple levels. So now we're going to look at increasingly complicated models and show that we can use this same ANOVA framework to do inference even when the models get much more complicated than the 2 or 3 or 4 parameter models that we've seen so far. So in order to demonstrate this, we're going to look at this data set that was published recently from my lab in collaboration with Todd Stuck, who is a member of the biology department here at UNC Charlotte. And this work was done by Josh Stokel, who at the time was a graduate student, PhD student in Todd Stuck's lab. Josh, unfortunately, has passed away since this paper has come out, but this represents this important contribution that he made represents his work and the quality of this data set, and you'll see it's an incredibly informative and interesting data set, and the quality of this data set really reflects how hard Josh worked during his PhD dissertation. So this data set is from a single cystic fibrosis patient exposed to an antibiotic regime over a period of about 3 years. So cystic fibrosis is a genetic disease among Caucasians in Europe and America. It's the genetic disease with the highest mortality rate among Caucasians. It's a disease which is caused by a defective ion channel, a chloride channel. Because this chloride channel is defective, it leads to salt imbalances in the lungs, which lead to fluid imbalances. Because of these fluid imbalances, patients with cystic fibrosis have trouble clearing their lungs, and bacterial infections tend to accumulate in the lungs. So this patient had repeated exacerbations. So exacerbations are a period where there's a flare-up of symptoms, and they were treated with antibiotics. And so what we're going to be looking at is longitudinal sampling over time treated with antibiotics as shown in this graph. The data are available. You can grab them here. You can grab the paper if you're interested in reading in detail about the analyses that we're going to do and about this data set at this link here from the Journal of Clinical Microbiology. The data, when you download them, will look like this. So this is a longitudinal data set. It starts on day 0. So this is within round-off error of 0. So we have a data set over time. There are different treatment categories. So there's before treatment. So this is before an exacerbation, immediately before an exacerbation. There's a stable period in between exacerbations. There's during treatment, so that's when antibiotic treatment was actually happening. And then there's a recovery period post-treatment. So you can see here there's a data set in relationship with time. So the x-axis has time. And the y-axis is qPCR data showing the absolute abundance of Burkholderia, which is a pathogen. So what you're watching on this patient is an increase in pathogen load as the patient progresses through the disease, as bacterial load increases and the patient gets sicker. So we're going to build and evaluate a series of linear models looking at these data. So you can see that there's a clear increase with time, and that's the first thing that we're going to do, the first model that we're going to build. But we can also use models to ask whether there's differences in bacterial load between these different conditions. And biologically, that means is this Burkholderia responding to antibiotic? Right? So is the bacteria lower during the treatment when there's antibiotic than at other time points? So we'll build and evaluate a series of linear models to ask these biological questions of this data set. So first we'll look only at time. So this is a simple linear regression model. And so this model has the Burkholderia concentration, or the Burkholderia absolute abundance on the y-axis, and the slope and an intercept the way linear models do. We can see that both the slope and the intercept are highly significant. Now, we don't care about the intercept, but the slope we do care about, so that's the null hypothesis that the Burkholderia is not changing with time. But clearly the Burkholderia is changing with time. The slope is not 0. So that comes back with a small p-value here. And we can explain about 56% of the data. The r-squared's 0.56. So we're able to explain 50% of the total Burkholderia absolute abundance data just as a function of time. And now we're going to consider as our first full model, a model with interaction terms. So we're now going to add treatment. So this model here, the simple linear regression, does not have treatment. It only has time. Remember that treatment is a categorical variable with 4 levels: before treatment, recovery, stable, and treatment. So we can actually get a very complicated model. It turns out that all we have to do in R to get a really complicated model is type this in R. Right? So I just say, I read in the data, and then when I build the linear model, I say this is log Burkholderia is a function of sample days star treatment. So the star here means interaction terms, right? So we're going to include interaction terms. So we're going to include both sample days in the model. Treatments is a factor here, and I'm going to have actually the treatment itself be the background. So remember that we're going to, in R, we have to specify what we want to be the background when we have these multiple levels. So I'm using relevel here so that the treatment time itself, at the time on the antibiotic, is the background. And then I tell R that that's a factor, although it knew that. And so now this star here means that I want both the time in days and the treatment, which is a categorical variable. And I want the interaction terms between them. So this doesn't look like I've done very much work here. I've just typed sample days star treatment. But as we'll see in a second, this is the model that actually gets produced in R. So this is actually a 8-parameter model where all of these parameters are here. To look at this in more detail, we can, as always, ask R to give us the data matrix. So we set x equals true when we build the linear model, and then we just inspect the x data matrix. So we have our 8 parameters here. The first parameter is going to just be the intercept, as always, just a series of 1s that's there. The second parameter is time in days. That's round off error within 0, and then time in days. Then we have our first series of dummy variables. The dummy variables are before treatment, recovery, and stable, because remember we set the treatment as the background in the previous slide on the relevel. And we can see the dummy variables are encoded as 0 or 1s, right? So this is 1 if you're before treatment, otherwise 0. This column is 1 if you're recovery, otherwise 0. This column is 1 if you're stable, otherwise 0. So these are dummy variables encoded in the way that we've seen the dummy variables for the ANOVA encoding of the t-test or the one-way ANOVA. And then we have these interaction terms, which is maybe something new, but mathematically is just multiplying the dummy variable times the number of days. So this is either 1 times the number of days if the dummy variable is set to 1, or otherwise it's 0. And we have 3 of those columns as well. Now we have an 8-parameter model, and we can visualize our full model as being 4 lines, each with independent slopes or and intercepts. So our full model, because it has 8 parameters, you're drawing 4 lines through the data, right? You have these 4 different treatment possibilities, treatment status possibilities. You're going to draw 4 lines through the data, and you're going to allow those lines to have independent slopes and intercepts. So there's 4 possible lines that you could draw. If each line has a slope and an intercept, there's 8 total parameters, and those correspond to the 8 parameters of these that we see in our data matrix here. The reduced model, by contrast, would get rid of the interaction terms. So if I got rid of the interaction terms, then I have a 5-parameter model. And we can think of this 5-parameter model as being 4 lines, each with a common slope. So there's only 1 slope and 4 different intercepts. So the 5-parameter model, which is going to be our reduced model for our first ANOVA test, is going to consider 4 lines each with identical slopes but differing intercepts. And our 8-parameter model is going to consider 4 lines each with a different slope and with a different intercept. So in R, we can generate these 2 models very concisely. The full model, we say star. We want these interaction terms. The interaction terms here, again, we mean as that each model, each treatment category can have its own slope. Or we can have the reduced model where we don't allow in interaction terms. And in our syntax, we just make this, we say this as a plus instead of a star. So in the reduced model, B5 and B5 through B7 are just always set to 0. And our first ANOVA is going to compare the full model to the reduced model. And so, again, at the matrix level, this is the full model. We can calculate, we could go through and calculate this error by hand, but we're just going to let R do this instead. So R gets the fits for us, and we just say sum residual, the sum residual squared of this model, and this turns out to be 33.8. There's 130 data points in the data set. There are 8 parameters in our full model. So we have our residuals, and we have our degrees of freedom for the full model. The reduced model has only these 5 parameters because parameters 6, 7, and 8 are no longer there. So the reduced model has only these 5 parameters. Again, I can make the reduced model in R, do the same thing, make the residual sum squareds, calculate that out. And I know there's 125 degrees of freedom in this reduced model because there's 130 data points and 5 parameters. So I crank through here and I just plug this into my usual formula. Remembering that the formula is the ratio of the difference between the models divided by their difference in degrees of freedom, divided by the full model divided by that degrees of freedom. So I just crank all of these numbers into R, and I get a p-value of 0.059. Alternatively, with much less typing, I can get that 0.059 by just saying ANOVA of the full model, right? So if I make this my full model, and I say ANOVA full model, R is going to tell me whether the interaction terms are significant, and I get that same p-value of 0.059. So this p-value of 0.059 I can get with much less typing by just building the full model and saying ANOVA full model. Now this is so this 0.06 there's sort of a marginal effect, right? So when we compare this model and this model maybe explains a little bit of the variance. It's at p equals 0.06. It's not like it doesn't explain any of the variance, but it's just over that 0.05 threshold. And so I'm quite happy to take the simpler model here and not deal with this more complex model that's there. And I think that's consistent with just sort of eyeballing the data. So if I just look at all of these data, it doesn't really seem obvious to me if I were to draw 4 lines for each one of these different colored data points that there are obviously different slopes between the different models. So I'm going to take the fact that we just crept over 0.05 and push forward with the reduced model. So going forward for the rest of this lecture, I'm going to not consider this. I'm going to not consider the full model that's here and consider this the reduced model here of having only these 4 lines with a common slope. Now, when you have a full model, you can then ask the next question is, well, maybe we can reduce the model further. So if this becomes our full model, so we're throwing away the 8-parameter model, and now we're going to go to a 5-parameter model. So our 5-parameter model says that there are 4 lines here with different intercepts, but identical slopes. And then the question that we're going to ask next is, when we compare this full model to a reduced model with just one slope, do we see a statistically significant difference between the 2 models? So the full model here is now just this 5-parameter model with no interaction terms. So there's an intercept, there's time, and then there's 3 dummy variables encoding our different conditions. And we're going to compare this to a reduced model that only has a slope, right? That doesn't care about the treatment conditions. Right? So the reduced model has 2 parameters. It has B0, B1. The full model has 5 parameters. And is there a difference between these 2 models? So same thing. I can now, my full model now used to be my reduced model, but now it's my full model. So my full model has this plus term, but no interaction terms. My reduced model doesn't have the treatments in it at all. It's just a simple linear regression. And so I can grind through, calculate the residuals here. The difference between the degrees of freedom in the models is 3 because you're comparing a 5-parameter model versus a 2-parameter model. The full model has 5 degrees of freedom. There are 130 data points. So there's 125 degrees of freedom because there's 130 data points minus the 5 parameters of the full model. When I use PF here, I get this 0.002, and this 0.002 corresponds to there. So with much less typing, I can recover what R is telling me if I just do the ANOVA of the full model, where the full model does not have the interaction terms. So we would argue the treatments do make a difference. So it does matter. The antibiotics do something in this subject. So we don't have to accept the reduced model. Just like in a one-way ANOVA, where the null hypothesis is the mean equals 0 the mean 0 equals the mean 1 equals the mean 2 equals the mean 3 equals the mean 4 equals the mean 5. The one-way ANOVA tells you whether that null hypothesis that all the means are equal. It gives you a p-value evaluating that null hypothesis, but it doesn't tell you for any particular pair of means whether they're different. Similarly, our one-way ANOVA, or ANOVA that we just performed, told us that the 4 treatment categories make a difference, but they don't say which one is different. So when I just type ANOVA full model, I get a p-value saying the treatments make a difference, but R doesn't tell me from just this ANOVA analysis which of the treatments made a difference. I can get that information potentially by typing summary of the full model instead of ANOVA full model. Remember that summary is pushing us to the statistics based on inference on the t-values. Right? And rather than using the summary view here, rather than taking the 3 dummy variables and making them all have coefficients of 0, the summary view here looks at them one at a time. Right? So remember that the beta coefficients of each one of the dummy variables is going to be how much does that dummy variable differ from the background. Right, so the background intercept the background intercept for treatment was 6.62. Right, so if we were to work our way backwards for treatment, which is our backgrounds, it was 6.62, and each one of those dummy variables, each one of these dummy variables, coefficients for the dummy variables, in our matrix equation in here. Right, so the treatment intercept was 6.62. Each one of these coefficients B2, B3, and B4 are going to be the difference of the intercept for each one of these variables. Right? So it's the difference of the intercept for each one of these variables. If I can find the data here. Right, so treatment was our background. That's the black. That's 6.62. The coefficients for these 3 variables is going to be the difference in the intercept of these lines. So the null hypothesis for each one of these variables is that it's not that the slopes are different, it's that the intercepts are different. Right? So we're asking, once you put a common slope here, are the other treatment categories with respect to treatment significantly higher? Right? So treatment is when the patient was on antibiotics. Right? So when the patient was not on antibiotics, do you see more of the bacteria relative to when they are on antibiotics, which is when the treatment is? And we express that null hypothesis not as a difference in slope, because in our simpler model, there's only one slope. This line only has one slope. Right? This is the model that we're considering. So there's only one slope. The question is whether these intercepts are different. And so R is giving us inference on that hypothesis that the intercepts are different relative to the treatment, because this estimate of the beta coefficient is the difference in the intercept between each one of these conditions and the background treatment intercept. Right? And so the null hypothesis is that these are 0, and we evaluate these null hypotheses with these p-values that are here using the t-statistic. And in this case, only one of them comes out as higher. It's the recovery. So recovery is significantly higher than treatment, and we can interpret that as biologically as saying that the bug goes back once the antibiotic is stopped. That's a potential interpretation. Although this is a borderline result at 0.01, and it also importantly has not been corrected for multiple hypothesis testing. And you can see that we did 3 hypotheses here. So this is perhaps not a conclusion that is robustly supported by the data, but we could argue maybe that it's a conclusion that is consistent with the way the data are presented. As always, we can ask how well do we fit these assumptions of normality, and as always, we can use plot full model here, and R will give us the residual plot and check the residuals for normality with QQ norm, and you can see that in this data set that the assumption of normality seems quite reasonable, and so we don't feel that there is problems with these assumptions in our use of these models in this case. And in fact, if we look at the distribution of residuals and just use the KS test to evaluate them, we get a fairly large p-value. So we fail to reject a null hypothesis that the residuals are not normally distributed. So this assumption of normality seems reasonable in this case. Finally, we can use R to actually recreate the graph of our data. So here I make a vector that just holds the colors, different colors, and I just manually go through, and again, there's more elegant ways to do this in R, but speaking R as I do, with a strong Java accent, I just use a for loop to manually go through and assign colors to each of the conditions, right? And then I can plot them out and keep track of the colors. And then in terms of the modeling, I can use AB line here. So the AB line, again, remembering that treatment is my background line. So the first AB line here is going to give me my background line. And then remembering that the coefficients represent the difference in the intercept, right? So there's a constant slope. So all of these data points have a constant slope. And the null hypothesis that we're looking at, or these beta coefficients, are the difference from the intercept. So if I just manually create these intercepts here, I can create all the different AB lines in R. So this allows me to see all of the data points and then see where R considers each model line for the models that we've built. And these visualizations can be extremely useful in both building some intuitions about what our model is telling us, and in looking to see if we think there's systematic violations of the assumptions of the models.